It's a strange thing to think about, but what if everything you've ever experienced, every memory, every future plan, every second ticking by on the clock on your wall, what if it's all happening at once, right now? What if the universe is a gigantic cosmic movie that's already been filmed and we're just watching our little part of it? What if the past isn't gone forever and the future isn't something to wait for? It's all there, an eternal present. It's a shocking idea, isn't it? The kind of thought that can make your head spin just before you drift off to sleep. The universe is a really weird place, and the more we learn about it, the more we realize that what seems like common sense is often the complete opposite of reality. A funny little reality check for you. We're all hurtling through space on a giant rock at thousands of miles per hour, and you probably won't survive the cosmic ride. But hey, let's not dwell on that. Instead, let's lie back, get comfortable, and think about the universe in a way that just might change how you see everything. We're going to dive deep into a question that has puzzled philosophers and physicists for centuries. Is time real? This video is best enjoyed when you're relaxing, during meals, while having coffee, before bedtime, or simply unwinding after a long day of work or study. The information has been compiled from various sources. If there's anything inaccurate or in need of correction, please feel free to leave a comment. Before we get too deep, take a moment to drop your location and local time in the comments. It's kind of cool to think about all of us, spread out across the world, sharing this moment together. Okay, so you've probably always thought of time as a river. It flows in one direction, from the past to the future, carrying you along with it. It's a simple, elegant metaphor. You can't step into the same river twice, right? The moment is always new, always fresh, always moving forward. But modern physics, with its mind-bending theories and dizzying experiments, suggests this is just a comforting illusion created by our brains. The first major clue that our perception of time might be a little off comes from the very bedrock of physics, Albert Einstein's theories of relativity. Before Einstein, scientists, and pretty much everyone else, believed that time was absolute. A universal, unchanging clock that ticked at the same rate for everyone, everywhere. It was a backdrop against which all the events of the universe unfolded. Then came Einstein, with his revolutionary ideas about space-time. He showed us that time isn't a separate entity at all. Instead, it's woven together with the three dimensions of space, up, down, left, right, and forward, backward, to form a single, four-dimensional fabric called space-time. And here's the kicker. This fabric isn't a rigid, static grid. It's flexible and dynamic, capable of being stretched and warped. Imagine you have a big trampoline. That's space-time. If you roll a bowling ball onto the trampoline, the fabric sags and curves around it. Now, if you roll a marble nearby, its path will be curved by that sag. In this metaphor, the bowling ball is a massive object like a planet or a star, and the marble is a smaller object or even a beam of light. The gravity of the massive object isn't some invisible force pulling things in. It's actually the curvature of space-time itself, caused by the object's mass. This is why planets orbit the sun and why light bends around massive galaxies. But it's not just space that gets warped. Time does too. The stronger the gravity, the slower time passes. This isn't just a theoretical curiosity. It's a proven, measured fact. The GPS satellites orbiting the Earth have to account for this time-bending effect. They're in a weaker gravitational field than we are down here on the surface, Because of this, their clocks tick ever so slightly faster than ours. It's a tiny difference, but if we didn't correct for it, the GPS system would be off by several miles every single day. So, time isn't a steady, universal drumbeat. It's a variable tempo, dictated by gravity and speed. Your clock and my clock might not be synchronized, even if we started them at the exact same moment. So, is time real? The simple answer, according to relativity, is sort of. It's real, but it's not the simple linear thing we assume it to be. It's a flexible dimension, tangled up with space, and it can be stretched, compressed, and warped by the fabric of the universe itself. The philosophical implications of this are huge. If time can be warped, if it can speed up or slow down, then what does now even mean? Is my now the same as your now? Probably not on a cosmic scale. But if time isn't a river, then what is it? We'll dive into one of the wildest ideas in physics next, something that might make you question whether your past, your present, and your future are all just one single, unchanging moment. So, if time isn't a flowing river, what is it? Let's take that thought from the end of the last section and really dive into it. Imagine for a moment that the universe isn't a story unfolding, but a giant static block. This is the block universe theory, and it's a mind-bending consequence of Einstein's theory of relativity. In this view, all of time, the past, the present, and the future, is equally real. Everything that has ever happened and everything that will ever happen exists simultaneously in a four-dimensional block of space-time. Your first kiss, the moment you're reading this right now, and the day you take your last breath are all equally present in this cosmic block. They aren't separated by a flow of time. They are just different points in space-time, just as New York and London are different points in space. This idea challenges our most basic intuition. We feel like time is moving. We remember the past, and we anticipate the future. We can't go back and change things. This feeling of a single, special moment, called now moving forward, is called the A theory of time. It's the common sense view that time is dynamic, and that only the present is real. The past is gone, and the future hasn't happened yet. But the block universe, or the B theory of time, argues that this feeling of now is just a trick of our consciousness. Think of it like this. If you're watching a movie, you're experiencing it moment by moment. You see the characters act and the plot unfold. But the whole film already exists, from beginning to end, on the film reel or the digital file. The present moment is just the frame you're currently watching. In the block universe, we are the viewers, and our consciousness is the projector lamp illuminating one frame of space-time after another. This isn't just a philosophical debate. It's rooted in the mathematics of relativity. Einstein's equations don't have a special variable for now. They treat time coordinates the same way they treat space coordinates. If you ask a physicist where an event happened, they'll give you 3 space coordinates and 1 time coordinate, say x, y, z, t. The t is just another number, another dimension. It's not a special flowing entity. This is why some physicists, including Einstein himself, found the block universe a compelling and natural consequence of their work. Einstein, after the death of a close friend, wrote a now famous letter of condolence saying, "For us physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." A pretty heavy thing to say, right? But it sums up the core of this radical idea. So why does time feel so different from space? Why can we move freely through space, but only in one direction through time? You can walk forward and backward in your room, but you can only move forward in time. This is where things get really mysterious. The block universe doesn't explain our psychological arrow of time. It doesn't explain why our memories are of the past and our expectations are of the future. It simply says that these moments, past and future, are just as real as this one. It's a deep and open question in physics and neuroscience. What is it about our brains that makes us perceive a linear, unidirectional flow of time? Another consequence of the block universe is that it presents a challenge to our idea of free will. If the future already exists, then is it already determined? If all events are set in the cosmic block, from the Big Bang to the last gasp of a dying star, then your decision to continue listening to this right now was always going to happen. This is a very old philosophical problem, but the block universe gives it a powerful new scientific context. Are we just passive observers of a cosmic story that has already been written? Or is there something about the chaotic, probabilistic nature of the quantum world that gives us a way out of this predetermined prison? We'll get to quantum mechanics later, but for now, just chew on the idea that the universe might be a solid, unchanging thing, and our experience of change and time passing is just a feature of our consciousness. It's a humbling thought, isn't it? To think that the very foundation of our existence, the steady march of time, might just be a brilliant cosmic illusion. So, we've thought about time as a giant, unchanging block, where all moments are equally real. It's a heavy thought, isn't it? But let's rewind a little bit and focus on the engine that drives this whole idea. Einstein's theory of relativity. It's the scientific bedrock of the block universe, and it's full of fascinating and verifiable consequences for time itself. You're probably familiar with the core concept. The faster you go, the slower time passes for you relative to someone who is standing still. This is called time dilation. It's not a hallucination or a trick of the light. It's a real, measurable effect of the universe. Imagine for a second that you're an astronaut on a spaceship, zipping around in space near the speed of light. Let's say you're doing this for 5 years, according to the clock on your ship. When you finally come back down to Earth, you'd find that many more than 5 years have passed for everyone else. Maybe 10, 20, or even 100 years, depending on how fast you were going. All your friends would be old and gray, and the world would have changed dramatically. This isn't science fiction. It's a prediction of Einstein's theory, and it has been proven time and again with incredibly precise clocks. We've even done it with airplanes. In a famous experiment, physicists flew an atomic clock around the world on a commercial jet, and then compared it to an identical clock that stayed on the ground. When they compared the two, the flying clock had ticked ever so slightly slower. The difference was minuscule, just a fraction of a second, but it was exactly what Einstein predicted. But why does this happen? The core idea is that the speed of light in a vacuum is the ultimate constant in the universe. It's the cosmic speed limit, and nothing can go faster. Everything else is relative to it, including time and space. As you speed up, your motion through space increases, and to keep the speed of light constant for all observers, your motion through time has to slow down. It's like a fixed budget. You have a fixed amount of space-time to spend. The more you spend on moving through space, the less you have to spend on moving through time. So, to a stationary observer, your clock seems to slow down. This is a deep dive into the very nature of reality, and it's a bit of a brain teaser. It means that the universe doesn't have a single universal now. Your present moment is different from the present moment of someone zipping through space in a rocket. This is why the idea of a block universe, where all moments coexist, makes so much sense to physicists. If there's no universal now, then what makes this specific instance so special? From the perspective of the block universe, the past and future are just as real and just as present as your now. Just as a different city is just as real as your current location. The second part of Einstein's relativity, general relativity, adds another layer to this. We talked about it briefly in the first section, but it's worth revisiting because it's a major mystery in science. Gravity doesn't just bend space, it also bends time. The stronger the gravitational pull, the slower time passes. This is why the clocks on GPS satellites, which are in a slightly weaker gravitational field than we are on Earth, tick a little faster. We have to constantly correct for this gravitational time dilation to make sure your GPS is accurate. This is a very cool, very real-world application of this crazy theory. So, here's a fun thought experiment for you. Imagine you're standing on the surface of a neutron star, an incredibly dense and massive object. The gravity there would be so strong that time would slow down dramatically for you. To an observer on Earth, you might seem to be moving in slow motion. A minute for you could be an hour, or a day, for someone far away. This leads to a fascinating scientific mystery. What happens to time at the event horizon of a black hole, where gravity is so strong that not even light can escape? From our perspective, time for anything falling into a black hole seems to slow down to a complete halt as it approaches the event horizon. It's an open question. Does time actually stop, or does our perspective just get weird? We've talked about how gravity and speed can warp and stretch time, and how the block universe suggests the past, present, and future might all be equally real. It's a lot to wrap your head around, I know. But just as you're getting comfortable with that idea, let's introduce the wild child of physics, quantum mechanics. If relativity gave us a universe with a wobbly, flexible timeline, quantum mechanics threatens to take time away from us entirely. It's a deep, open mystery that keeps some of the smartest minds on the planet up at night. The question isn't just, is time real? But is time even a thing at all? In the world of quantum mechanics, we're dealing with the smallest things in the universe: atoms, photons, and electrons. Down at this tiny scale, reality gets unbelievably strange. Particles don't have a single location or a single speed. They exist in a superposition of all possible locations and speeds at once, like a ghost haunting every point in a room simultaneously. It's only when we measure them that they choose a single state. This is the famously weird Copenhagen interpretation, which suggests that the act of observation fundamentally changes reality. But here's the part that really messes with our concept of time. The fundamental equations of quantum mechanics, like the Schrödinger equation, don't have a special direction for time. They work just as well going forward as they do going backward. This is a huge contrast to our everyday experience, where time clearly moves in one direction. We can't unbreak a coffee cup or unscramble an egg. But according to these core quantum equations, there's no reason why these things couldn't happen. It's a deep and unresolved paradox, often called the problem of time. It suggests that time might not be a fundamental property of the universe at all, but rather something that emerges from the behavior of a vast number of particles acting together. Think of it like this. A single water molecule doesn't have a temperature. It just has motion. But when you get a massive number of them together, their collective motion gives rise to the property we call temperature. Maybe time is the same way. Maybe it's a property that only emerges from the interactions of countless quantum particles, and down at the most fundamental level, time doesn't exist. So, where is time in the quantum world? One of the most famous and unsettling thought experiments that gets at this is the Wheeler-DeWitt equation. This is a theoretical equation that tries to combine general relativity and quantum mechanics into a single theory of everything. When you solve this equation, a very strange thing happens. The time variable, the t, that we're so used to, disappears entirely. This has led some physicists to suggest that the universe, in its most basic form, is timeless. It's an eternal, unchanging thing. Our sense of a flowing past, present, and future is just a feature of our own consciousness, a cognitive trick that helps us make sense of the world. This leads to a really interesting scientific debate. Is time an illusion, a convenient fiction our brains have created? Or is there something we're missing in our quantum equations? Perhaps there's some yet-to-be-discovered force or mechanism that gives time its direction. The quantum world is full of these kinds of mysteries. For instance, the phenomenon of quantum tunneling allows a particle to pass through a barrier it shouldn't have the energy to cross. We've even observed particles that seem to arrive on the other side of the barrier before they even begin their journey. It's a spooky result that, if taken at face value, seems to suggest time is being played with at a fundamental level. While the jury is still out on that particular interpretation, it shows just how weird the universe is when you zoom in close enough. Maybe, just maybe, the flow of time is only a property of the macroscopic world, and the universe, at its most basic level, is a single, timeless, eternal moment. It's an idea that's as beautiful as it is terrifying, and it's one of the central mysteries of modern physics. So, we've gone from the block universe, where all of time exists at once, to the quantum world, where time might not exist at all. It's a dizzying journey, and the weirdness doesn't stop there. One of the most mind-bending phenomena in quantum mechanics, and one that seems to completely defy our everyday sense of time, is quantum entanglement. This is the part of the show where you might need to take a deep breath, because it's a bit of a head-scratcher, even for the experts. Here's the core idea. Two or more particles can become entangled. When they are linked in such a way that the state of one instantly affects the state of the other, no matter how far apart they are. Imagine you have two quantum coins. They are entangled so that if one lands on heads, the other must be tails, and vice versa. Now, you take one of these coins to the other side of the universe, and I keep the other. The moment I flip my coin, and it lands on heads, yours, trillions of miles away, instantly becomes tails. There's no signal sent between them. There's no delay. It's an instantaneous connection. This is a proven mainstream science fact. It has been demonstrated in countless experiments. And it's so weird that even Einstein, who was a genius with a powerful imagination, called it spooky action at a distance. Why? Because it seems to violate the cosmic speed limit. Remember that the speed of light is the fastest anything can travel. If information could be sent instantaneously across the universe, it would mean we could send a message faster than light. This would completely break our understanding of causality, the idea that a cause must come before its effect. If information travels faster than light, you could, in theory, send a message to the past, which is a major no-no in physics. So how does entanglement work without breaking this rule? This is where the scientific mystery deepens. The prevailing theory is that entanglement doesn't actually allow us to send information faster than light. You can't use it to tap out a message in Morse code to your buddy on a distant planet. When I measure my coin and it lands on heads, I don't know what your coin is until you call me on the phone at the speed of light and tell me. But the link itself, the spooky correlation, seems to be timeless. It's as if the two entangled particles exist in a shared, timeless reality where the usual rules of space and time don't apply. Their fate is linked from the moment they were created, and that link seems to exist outside of the flow of time.
This brings us back to the block universe idea. What if the entangled particles' outcomes aren't determined at the moment of measurement at all? What if their states were already fixed from the beginning of time in the four-dimensional block of space-time? In this view, entanglement isn't about spooky action at a distance. It's about revealing a pre-existing static reality. It's like having two halves of a torn photograph.
If you look at your half, you instantly know what's on the other. Not because information traveled, but because the photo was a single, unified thing from the start. That's one way to think about it. Another open scholarly debate is whether this instantaneous connection is a hint that there's a deeper, more fundamental reality that underlies our perception of space and time. Maybe space and time aren't the bedrock of the universe at all, but are just emergent properties. Maybe at a deeper level, everything is connected in a timeless, unified web. This is the goal of many theoretical physicists, to find a theory of quantum gravity that unites relativity with quantum mechanics. Entanglement is a key piece of this puzzle, a hint that our current understanding of time and distance might be incomplete. The fact that a measurement here can instantaneously affect a particle over there suggests that here and there might not be as separate as we think they are. It's a beautifully strange concept, suggesting a universe that is far more interconnected than we ever imagined. Okay, so we've messed with time, maybe even made it disappear in the quantum world. But there's one thing we haven't touched on yet, a simple, undeniable fact of life. Time moves forward. You can't unring a bell, you can't put the toothpaste back in the tube, and you can't reverse the flow of time. This is what physicists call the arrow of time, and it's one of the most persistent and puzzling mysteries in all of science. Why does time have a direction?
You've probably heard of the second law of thermodynamics. It's the law that governs how things change in the universe, and it's the most likely candidate for explaining the arrow of time. The law states that the entropy of an isolated system can only increase over time. Entropy is a measure of disorder or randomness. Think about a neat pile of bricks. If you throw them in the air, they'll land in a messy, disordered pile. They won't spontaneously reorganize themselves into a neat pile again. That's the second law of thermodynamics in action. Things naturally move from order to disorder. The universe, left to its own devices, is constantly getting messier. So how does this relate to time? Well, if we think of the universe as a giant isolated system, it started in a state of incredibly low entropy. The Big Bang, our best theory for the beginning of the universe, created a very hot, dense, and uniform state. It was a state of immense order. Since then, the universe has been expanding and cooling down, and its entropy has been increasing. Stars have formed and died, galaxies have clumped together, and complex life has emerged. All of these processes are increasing the overall disorder of the cosmos. The arrow of time, then, is simply the direction of increasing entropy. It's the direction from the neatly organized Big Bang to the messy, disordered future. We can't go back in time because that would mean a decrease in entropy, a violation of the second law of thermodynamics. It would mean the universe would have to spontaneously get more ordered, and that just doesn't happen. This is a mainstream science fact, but it leads to a profound and open scientific mystery. Why did the universe begin in such a low entropy state? It's a bit like finding a perfect, untouched sand castle on a beach and asking why it isn't already a messy pile of sand. To get to the high entropy state we see today, the universe must have started from a very special, very low entropy beginning. What caused that initial state? We don't know.
The Big Bang Theory describes the expansion of the universe from this point, but it doesn't explain what created that point in the first place. Some physicists believe that this mystery is the key to understanding the ultimate nature of time itself. Another debate is whether the second law of thermodynamics is the cause of the arrow of time or just a consequence of it. Is entropy the reason time moves forward, or is it just the way we observe the universe moving forward in time? Some physicists argue that the arrow of time is a deep, fundamental property of reality, and entropy simply follows along. Others argue that without entropy, there would be no way to distinguish the past from the future, and therefore no arrow of time. It's a classic chicken and egg problem. Regardless, the second law of thermodynamics gives us a powerful physical reason for why time seems to move forward. It's not just a feeling, it's the fundamental tendency of the universe to go from order to disorder. When you watch an ice cube melt in a glass of water, you're not just seeing a simple change of state. You're watching the arrow of time in action, an undeniable one-way journey toward a future of greater entropy. So, we have a physical arrow of time driven by the universe's march toward disorder. It's a powerful and elegant idea, but it doesn't fully explain our personal, deep-seated feeling of time. Why do we feel like time is moving forward? Why can we remember the past, but not the future? The answer to that question lies not in the stars, but inside your own head. Your sense of a flowing, linear timeline is, to a huge extent, a construct of your memory. Think about it this way. Your brain isn't a video recorder, storing a perfect continuous film of your life. That's a fun thought, but it's not how it works. Instead, your memories are like a collection of snapshots or fragments of a story stored in different parts of your brain. When you remember something, your brain is actively reconstructing that event from those fragments. It's a creative process, a bit like a storyteller weaving a narrative from a few key details.
This is why memories can be unreliable, why they can change over time, and why we can sometimes create entirely false memories without even realizing it. The past isn't a static place we visit. It's a dynamic, ever-changing story we tell ourselves. This is a mainstream science fact, and it gets at a really interesting, open scholarly debate. Is the feeling of time passing an emergent property of our consciousness? Our brain takes in a constant stream of sensory information from the world. It processes this information, organizes it into a coherent narrative, and creates a sense of a now. Then it stores some of this information as memories, creating a past we can refer back to.
The act of creating this narrative, of linking events together in a before and after sequence, is what gives us our subjective sense of time. Without memory, would we have a sense of time at all? If you couldn't remember what happened a moment ago, would you even know that a moment had passed? It's a fascinating question.
There are many different kinds of memories, and they all contribute to this feeling. Episodic memory is your personal diary, your memories of specific events and experiences, like what you had for breakfast this morning or your first day of school. Semantic memory is your mental encyclopedia, full of facts and concepts that aren't tied to a specific time, like knowing that the sky is blue. Together, these different types of memory allow us to build a rich, continuous narrative of our lives. The subjective experience of time is also influenced by our emotional state. Have you ever noticed how time seems to fly by when you're having fun, but drags on forever when you're bored or waiting for something? This is a great example of how our internal biological clock, which we'll get into later, can be influenced by our mental state. It's not that the clock is actually slowing down or speeding up. It's that our brains are allocating their resources differently.
When you're having fun, your brain is focused on the activity, and it doesn't have much left over for monitoring the passage of time. But when you're bored, your brain is actively looking for things to do, and the lack of new information makes the passage of time seem painfully slow. So, when you're lying in bed right now, thinking about what you did today, what you're really doing is using the complex, intricate machinery of your brain to reconstruct a story from memory. You're creating a past that feels real and solid, even though it's just a collection of firing neurons. It's a beautiful, elegant illusion, and it's what makes us feel like we're moving forward in time. But remember that this is just one piece of the puzzle. The brain creates our subjective sense of time, but the universe itself has a few more tricks up its sleeve. We've seen how memory creates our personal sense of the past, but what about the future? We spend a lot of our time anticipating it, planning for it, and worrying about it. The future to us feels open and full of possibilities. We can make choices that will shape what happens next. This feeling that our actions today are creating the future is at the heart of our sense of free will.
But is it real, or is the future just as fixed as the past? This is one of the oldest philosophical and scientific debates, and modern physics has only made it more complicated.
On one side, you have the idea of determinism. This is the belief that every event, including every choice you make, is the inevitable result of previous causes. If we knew the exact state of the universe right now, the position and velocity of every single particle, we could, in theory, predict the future with perfect accuracy. It's like a cosmic game of billiards. If you know how the balls are arranged and the exact force of the cue ball, you can predict exactly where every ball will go. In a deterministic universe, the future isn't open, it's already written. This idea gained a lot of traction in the era of classical physics, where the universe was seen as a giant, predictable machine. If the block universe theory we discussed earlier is correct, where the future already exists, then the universe is by its very nature deterministic. Your future wasn't something you created. It was always there, waiting for you to get to it. On the other side of this debate, the one that gives us hope for free will is quantum mechanics. The quantum world is not deterministic. It is inherently probabilistic. When we talk about a particle's position or velocity, we can't know both with perfect certainty. This is the famous Heisenberg uncertainty principle. We can only calculate the probability of a particle being in a certain place. It's not that our instruments are bad, it's a fundamental feature of reality at the smallest scale. Particles exist in a state of potentiality, and it's only when they are measured or observed that they choose a specific state. This element of pure, fundamental randomness, some physicists and philosophers argue, is where free will comes from. The universe isn't a perfectly predictable machine. It's a game of chance at its core. The great mystery here is how these two ideas, the seemingly deterministic macro world and the probabilistic quantum world, fit together. The laws of classical physics, which govern our everyday lives, are incredibly good at predicting things. We can launch a rocket to the moon and predict exactly when it will get there. We don't have to worry about a rocket suddenly appearing on the other side of the solar system due to a quantum fluctuation. But does that mean the quantum randomness is somehow averaged out at our scale?
Or is it possible that this randomness, these little moments of unpredictability, are amplified in our brains to give us the feeling of free will? This is a huge and open scholarly debate. Some physicists, like Stephen Hawking, argued that even with quantum uncertainty, the universe is fundamentally deterministic. They believe that even if we can't predict the future with 100% certainty, it doesn't mean that the future isn't already set. It just means our ability to know it is limited.
On the other hand, many others believe that quantum randomness provides a genuine physical basis for a future that is not yet written, a future that we can, at least in part, create through our choices. So, when you're thinking about what you're going to do tomorrow, remember that you are grappling with one of the deepest questions in all of science and philosophy. Is the future an open road or a predetermined path?
The future is an open question, and it's a deeply personal one. But the past? That seems completely locked down. Or is it? We've talked about time being flexible, and how the block universe suggests the past is just as real as the present. This brings us to one of the most popular and most paradoxical ideas in all of science fiction: time travel. The idea of hopping into a machine, pressing a button, and zipping back to ancient Rome or forward to the year 3000 is a classic fantasy. But is it scientifically possible? And if it is, what are the rules?
Let's start with what we know for sure. We are all, in a sense, time travelers already. We're constantly moving forward in time at a steady rate. And thanks to Einstein, we know we can subtly manipulate that rate. As we discussed, if you travel at high speeds or are in a strong gravitational field, your clock will tick slower than someone else's. So traveling into the future is not only possible, it's a proven mainstream science fact. If you were to get in a spaceship and fly around at near the speed of light for a few years and then return to Earth, you would have traveled into the future. You'd be older, but everyone you know would be much, much older. You'd have experienced less time, and for you, the future would have arrived sooner. It's not a fantasy. It's a consequence of the way the universe works.
But what about going backward? Traveling into the past is a whole different ball game. This is where the paradoxes and the scientific roadblocks pile up. The most famous of these is the grandfather paradox. The thought experiment goes like this. You build a time machine, go back in time, and kill your grandfather before he meets your grandmother. If you succeed, then your parents would never have been born, and neither would you.
So, how could you have gone back in time to kill him in the first place? It's a logical knot that seems impossible to untangle.
This leads to a huge, open scholarly debate about how time travel, if it were possible, would even work. One idea is the Novikov self-consistency principle. It suggests that if you were to travel to the past, you wouldn't be able to change anything. The universe would find a way to prevent you from creating a paradox. Maybe you'd try to kill your grandfather, but the gun would jam, or you'd slip on a banana peel, or a stray dog would bite you at the exact wrong moment. The universe would conspire to make sure that, whatever you did, it would be consistent with the timeline you already knew. So, you could go back in time, but you wouldn't be able to change the past. You would simply be a part of the past, just another character in the story that had already been written.
Another theory, and one that's a lot more fun, is the many worlds interpretation of quantum mechanics. This idea suggests that every time a choice is made, the universe splits into different parallel timelines. If you went back in time, you wouldn't be traveling to your own past. You'd be creating a new parallel universe, a new branch of reality with your actions. So, you could kill your grandfather, but it wouldn't affect your original timeline.
It would just create a new timeline where he died and you were never born. This neatly sidesteps the grandfather paradox, but it means that the past you leave behind is forever sealed and unchangeable.
So, while traveling to the future is a reality, traveling to the past is currently impossible with what we know. The energy required to create a time machine, like a wormhole or a closed time-like curve, is so vast that it's far beyond our current technological capabilities. So, for now, time travel to the past remains firmly in the realm of science fiction. The past is a memory, the future is an anticipation, and the present is all we have.
But the fact that we can even discuss these paradoxes with some scientific rigor is a testament to how strange and beautiful the universe really is. We've explored time on a human scale, from our memories to our wild dreams of time travel. But what about the ultimate timeline, the one that governs the entire universe? On a cosmic scale, time is a different beast altogether. It's a grand, sweeping story that began with a moment of creation and, as far as we can tell, will end in a slow, cold fade. This is the story of cosmic time, and it's what gives context to our little, fleeting lives. Our current understanding of the universe's timeline begins with the Big Bang. This is a mainstream science fact, supported by a wealth of evidence, from the expansion of the universe to the cosmic microwave background radiation. According to our best models, the universe began about 13.8 billion years ago from an unimaginably hot, dense point. At that moment, space and time themselves came into being. Before the Big Bang, there was no before. There was no time. The universe has been expanding and cooling ever since, forming galaxies, stars, and planets along the way. This is the cosmic clock ticking forward, and it's driven by the same arrow of time we talked about earlier, the inexorable increase of entropy. The universe is going from an incredibly low entropy, ordered state to a high entropy, disordered state.
This grand cosmic story has a few key moments, like the formation of the first stars, the birth of our own solar system about 4.6 billion years ago, and the emergence of life on Earth. But it also has a few possible endings, and they are not exactly cheerful. The future of the universe is an open scientific mystery, and there are a few competing theories for how it all ends. The first, and most likely, is called the heat death, or the Big Freeze. In this scenario, the universe continues to expand forever. As it expands, everything gets further and further apart, and the universe cools down. Eventually, all the stars will burn out, all the galaxies will drift away from each other, and all that will be left is a cold, dark, empty void. All the energy will have been spread out so thinly that nothing can happen anymore. Entropy will have reached its maximum point, and time, for all intents and purposes, will have ceased to have any meaning. It's a bit of a grim ending, isn't it? A slow, cold, silent death for all of existence. Another possibility is the Big Crunch. In this theory, the expansion of the universe slows down and eventually reverses. Gravity takes over, and everything starts falling back toward a central point. All the galaxies collide, the universe gets hotter and hotter, and it eventually ends in a state similar to the Big Bang, just in reverse. Some physicists even wonder if this could lead to a new Big Bang, a cyclical universe that expands and contracts forever, like a cosmic breath. A third, more dramatic theory is the Big Rip. This is a more recent idea, based on our discovery of dark energy, the mysterious force that is accelerating the expansion of the universe. In this scenario, dark energy gets stronger and stronger over time, eventually overpowering all other forces including gravity. Galaxies would be ripped apart, then solar systems, then planets, and finally, even atoms themselves would be torn to shreds. Time would end when the very fabric of space-time itself is torn apart. So, while we're all busy with our little human lives and our personal perceptions of time, the universe is ticking along on its own grand cosmic clock. It started with a bang and will end in either a whimper, a crunch, or a rip. It's a humbling thought, a quiet reminder that our own lives are just a tiny, fleeting moment in a story of unimaginable scale. Our time is limited, but the universe's time, at least for now, is still running. We've zoomed out to the cosmic scale, but now let's zoom back in, all the way into your own body. We've seen how our memories give us a personal sense of the past, and how our brains create a subjective feeling of time. But there's something else at play, a more fundamental biological clock that governs our lives. This is the realm of biological clocks and circadian rhythms, and they are a perfect example of how our bodies are deeply connected to the rhythm of the planet we live on. Have you ever wondered why you get sleepy at night and wake up in the morning? It's not just because the lights are off and the birds are chirping. It's because your body has a finely tuned internal clock, a master timekeeper called the suprachiasmatic nucleus, or SCN, located in your brain. This little bundle of nerves acts like a conductor, orchestrating all the rhythms of your body. It governs everything from your sleep-wake cycles to your body temperature, hormone levels, and even your mood.
This is a mainstream science fact, and it's something that scientists have been studying for decades. This master clock is primarily synchronized by light. When light hits your eyes, it sends a signal to your SCN, telling it to be on. When it gets dark, the SCN signals your pineal gland to produce a hormone called melatonin, which makes you feel sleepy. This natural cycle, a biological rhythm that repeats roughly every 24 hours, is called a circadian rhythm. It's so powerful that even if you were to live in a cave with no sunlight, your body would still try to follow a 24-hour cycle.
It's a testament to how deeply our biology is tied to the rotation of the Earth.
But this isn't a perfect system, and it leads to a fascinating, open scientific mystery. We're all familiar with jet lag. When you travel across several time zones, your internal clock is still set to your old location's time. You might feel sleepy in the middle of the day or wide awake at 3 a.m. It takes a few days for your SCN to resynchronize to the new light-dark cycle. This is a great, albeit annoying, example of how our biological clock can get out of sync with external time.
The mystery is, what happens when this clock is constantly disrupted? In our modern world of artificial light, shift work, and late-night binge-watching, we are constantly messing with our circadian rhythms. Scientists are still trying to figure out the long-term health consequences of this. We know that a disrupted biological clock can lead to a host of problems, from sleep disorders and depression to a higher risk of heart disease, and even certain types of cancer.
The scholarly debate is ongoing about how much of this is a direct result of the desynchronized clock, and how much is due to other factors that accompany these lifestyles.
So, while we might think of time as a universal, external force, your body has its own internal timekeeper, one that is as old as our species itself. It's a beautiful system, a tiny clock in your brain that is synchronized with the grand, steady rotation of the Earth. So the next time you feel a bit tired in the evening, remember that it's not just a feeling. It's your body's biological clock, a natural rhythm that governs your life and connects you in a very real way to the motion of our planet.
We've talked about the universe's timeline, from the Big Bang to the potential Big Rip. But what about the very beginning? What happened at the moment of the Big Bang? And perhaps, more fundamentally, what was there before the Big Bang? This is a question that pushes the limits of human knowledge and is a deep, open scientific mystery that has no satisfying answer. It's the ultimate chicken or the egg problem, and it forces us to confront the very nature of time itself. According to our current understanding of cosmology, the Big Bang wasn't an explosion in space, but rather the beginning of space and time themselves. Before that moment, all of the energy and matter in the universe was compressed into an infinitely dense, infinitely hot point called a singularity. As far as our physics can take us, at this singularity, all the rules break down. The laws of general relativity, which we use to describe gravity and the large-scale structure of the universe, simply can't handle a singularity. This is a mainstream science fact. Our current theories hit a wall. So, when you ask, what was before the Big Bang? The most common answer from a physicist is that the question doesn't make sense. If time began at the Big Bang, then there was no before. It's a bit like asking what's north of the North Pole. The concept is meaningless because you've reached the boundary of the system. But that answer, while logically sound within our current framework, is deeply unsatisfying. It leaves a gaping hole in our understanding. This is where the open scholarly debate really heats up. One idea is that our universe is just one of many, part of a larger multiverse. In this scenario, the Big Bang wasn't the ultimate beginning. It was just the birth of our particular universe from a pre-existing, timeless reality. Maybe there was a larger super time in which different universes are constantly being born and dying. We just happen to live in one of them. It's a bit like bubbles, forming and popping in a giant cosmic bathtub. Another idea comes from string theory and M theory. These highly theoretical frameworks suggest that our universe isn't the only dimension out there. They propose that we live on a brane, a kind of cosmic membrane, that exists in a higher dimensional space. The Big Bang, in this view, could have been the result of two of these branes colliding. This collision would have released a massive amount of energy, creating our universe and starting the flow of time within it. In this model, there was a before, but it wasn't a time as we understand it. It was a timeless, higher dimensional reality where these branes existed and moved. A third idea, and one that is just as mind-bending, is that the universe is a cyclical one, a repeating series of big bangs and big crunches. In this theory, the universe we live in is just the latest in an infinite sequence of universes. When our universe collapses in a big crunch, it will rebound into a new Big Bang, starting the process all over again. In this view, time never truly begins or ends. It's a continuous, eternal loop. So, while we have powerful tools to describe what happened after the Big Bang, the ultimate origin of time and the universe remains a mystery. We've pushed our understanding of physics to its breaking point, and we're left with a series of fascinating yet unproven ideas. Was the Big Bang the absolute beginning of time, or was it just the start of our chapter in a much larger and much more mysterious cosmic story? The answer is out there, somewhere beyond the boundaries of our current knowledge. So, if the beginning of time is a mystery, what about the end? We've already touched on the cosmic possibilities, the heat death, the big crunch, and the big rip. Each of these scenarios represents a different way
the universe's grand clock might stop ticking. But these are just theories, and the ultimate fate of the universe, and therefore the end of time, is a deep, open, scientific mystery. The question isn't just how it ends, but whether it ends at all.
Let's revisit the heat death scenario. This is the most widely accepted theory right now, given our discovery of dark energy pushing the universe's expansion ever faster. The universe will continue to expand, and as it does, it will get colder and emptier. All the stars will eventually burn out, leaving a sea of black holes and dead stars. These will slowly evaporate through a process called Hawking radiation, a mainstream science fact that suggests even black holes aren't forever.
Eventually, after an almost unimaginable amount of time, there will be nothing left but a thin soup of subatomic particles and photons, all spread out so far apart that no interactions can happen. Entropy will be at its maximum. In this state, there's no change, no events, no before and after. Would time even have meaning anymore? This is a philosophical puzzle as much as a scientific one. If nothing happens, does time still exist?
But what if something else is at play? A competing scholarly debate is whether the universe is just a temporary state of a more fundamental reality. Some physicists, including those working on string theory and loop quantum gravity, wonder if the universe isn't a continuous expansion and contraction, but a cycle. Maybe the universe we're in right now is just one of many, and after it reaches its end, it will somehow bounce back into a new beginning. This is often called the Big Bounce.
In this model, the big crunch of one universe would lead to the Big Bang of the next, and so on in an infinite loop. In this view, time never truly ends. It's a continuous, eternal cycle. The arrow of time would still exist within each cycle, but on a grander scale, time would be timeless. It's a very elegant and hopeful idea, isn't it? It suggests that even in death, there is the seed of new life.
And then there's the truly strange possibility tied to our discussion of quantum mechanics. What if the universe, at its most fundamental level, is timeless? In this view, the end of the universe isn't a final moment in time, but a transition to a different state of reality. Some physicists working with the Wheeler-DeWitt equation believe that the universe's true nature is static and unchanging.
The sense of time and change we experience is an emergent property, something that only exists because we are part of the system. So, at the end of the universe, maybe time doesn't stop. Maybe our conscious experience of time just fades away, and the universe returns to its true, timeless state. This is an incredible thought, suggesting that the end of time might just be the removal of the illusion of time itself. So, the ultimate fate of time is still very much up for grabs. Will it end in a cold, lonely silence where all change ceases? Will it loop forever, giving rise to new universes in an endless cosmic dance? Or will it simply dissolve, revealing the timeless reality that has been there all along? The mystery of time's end is just as profound as its beginning. We're living in the middle of a story whose ending has not yet been written.
We've explored time from the cosmic scale to the quantum realm, from the past to the potential end of the universe. But now, let's bring it all back to the one thing that ties it all together: your consciousness. The feeling of a continuous, flowing now is the central mystery of time, and it's something that we experience every waking moment. The very idea that you are a singular person moving through a singular timeline is a product of your mind. So, how does consciousness create time?
This is a deep and open, scholarly debate. a puzzle that sits at the intersection of neuroscience, philosophy, and physics. One idea is that consciousness is a constant process of predicting the future and then updating those predictions with new sensory information. Your brain isn't just passively taking in data, it's actively trying to figure out what's going to happen next, a fraction of a second ahead of time. It's building a model of the world, and this model is constantly being refined. The feeling of time passing, then, is the feeling of your brain constantly updating its internal model of reality. The now is the moment where your predictions meet reality. Another idea is that consciousness is what gives rise to the arrow of time for us personally. We've talked about how the universe's arrow of time is tied to entropy, the move from order to disorder. But our consciousness has its own arrow. It's a forward-moving narrative that our brain creates. Our memories are of the past, and our intentions are of the future. The feeling of a unidirectional flow of time is a direct consequence of the way our brains work. Without a brain to create this narrative, would there be a past, present, and future in our lives? Probably not. We would just be a series of disconnected, static moments.
The very concept of the present moment is a funny one. What is the now? Is it a single, infinitesimally small point in time? Or is it a duration? Neuroscience suggests that the now isn't a single point at all. It's a collection of moments, a window of time that our brain lumps together into a single present. The brain takes in sensory information from your eyes, your ears, and your skin, but it doesn't process it all at the exact same speed. Your brain has to work hard to stitch all this information together into a coherent picture of the world, a picture that feels instantaneous to you. The time it takes for this processing to happen, just a few hundred milliseconds, is the duration of your now. So, the present moment, as we experience it, isn't a single point. It's a short, continuous window of time created by your brain. This is a mainstream science fact, and it has some wild implications. It means that the now you are experiencing is already in the past. By the time your brain has processed all the sensory information and created a coherent picture, the actual moment you were observing has already happened. You are, in a very real sense, always living in the past, just a fraction of a second behind reality.
It's a bit of a trippy thought, but it's a great illustration of how our consciousness shapes our perception of time. The universe doesn't have a present moment, but we do, and it's a beautiful, elegant illusion created by the intricate workings of our brains. So, when you're lying in bed right now, thinking about all this, remember that your very ability to think about time is what makes time real for you.
We've just touched on the idea that the now you feel is a fraction of a second behind reality. It's a mind-bending thought, isn't it? The present moment is the cornerstone of our experience of time, yet it's also the most elusive concept in all of physics and philosophy. It's the point where the future becomes the past, but the moment you try to grab it, it's already gone. So, what exactly is the now, and why is it so hard to pin down? In the classical Newtonian view of the universe, the present moment was a universal shared reality. The now was the same for everyone, everywhere. But, as we've discussed, Einstein's theory of relativity shattered that idea. Because time is relative, and it can be stretched and warped by speed and gravity, there is no universal, single now. Your now and my now, if we are moving relative to each other, are not the same. This is a mainstream science fact, and it's a huge reason why the block universe theory is so compelling to physicists. If there's no universal present moment, then what makes this instant so special? The answer is that it's not special at all. It's just a point in the four-dimensional block of space-time that our consciousness happens to be experiencing right now.
This leads to a really interesting open scholarly debate. Is the present moment a fundamental feature of reality, or is it a complete illusion? The block universe model suggests it's an illusion. In that view, the universe is a static, unchanging thing. The feeling of now, moving forward, is just the way our consciousness perceives this static reality. It's like watching a movie, frame by frame. The entire movie exists on the film reel, but our experience of it is a continuous, unfolding story. The now is just the single frame we are currently watching. So, the present moment isn't a property of the universe, it's a property of our consciousness.
But there are other ideas. Some physicists argue that the present moment is real, and that the universe is constantly in the process of creating a new now. This view, sometimes called presentism, suggests that only the present is real. The past is gone forever, and the future has not yet come into being. In this model, the arrow of time is a fundamental feature of reality, a constant creation of new moments. The past doesn't exist, and the future is genuinely open. This view aligns with our everyday experience, but it's much harder to reconcile with the mathematics of relativity, where time is treated just like another dimension of space.
So, where does the truth lie? Is the present moment a real physical thing that is constantly being created, or is it a powerful illusion of our consciousness? We don't have a definitive answer, but we can see the physical evidence of how our brains construct a subjective now. A great example is the Libet experiment, a mainstream science fact that messes with our sense of the present. In this experiment, a person is asked to press a button and to note the exact moment they made the conscious decision to do so. Researchers found that the brain activity associated with the physical action of pressing the button occurred before the person was consciously aware of making the decision. It was only a fraction of a second, but it suggests that our conscious awareness of the now is a little behind the actual physical events. It's a bit like a post hoc rationalization. Our brain decides to do something, and then, a moment later, we become consciously aware of that decision, and we feel like we just made it. It's a great example of how our consciousness is constantly stitching together our experience of time, often a little bit after the fact.
We've been talking about the elusive present moment and how it's not a universal thing. This idea that time isn't a separate, absolute entity, but is instead intertwined with the three dimensions of space, is one of the most profound insights of modern physics. It's the concept of space-time, and it's a mainstream science fact that forms the bedrock of Einstein's theories of relativity. It's what gives the universe its structure, and it's why time can be stretched and warped. Imagine you're walking across a vast, flat field. You can go forward, backward, left, or right. Now, imagine a fourth dimension, time. In the classical Newtonian view, this would be like walking on that field while a separate, universal clock ticks in the background. Your movement on the field doesn't affect the clock, and the clock doesn't affect your movement. But in Einstein's universe, the field itself is different. It's not a flat, three-dimensional space with a separate time dimension. It's a unified four-dimensional fabric called space-time. And this fabric can be curved and distorted by mass and energy. A great analogy to think about this is a trampoline. If the trampoline is empty, it's a flat, two-dimensional surface. That's empty space-time. Now, if you place a heavy bowling ball in the middle, the trampoline sags. That's a massive object like a planet or a star, and its mass is curving space-time.
Now, if you roll a marble nearby, it won't go in a straight line. It will follow the curve in the trampoline, orbiting the bowling ball. That's not a force pulling the marble in. It's the curvature of space-time itself. This is the central idea of general relativity. It tells us that gravity isn't some mysterious force acting at a distance. It's the effect of mass and energy curving the very fabric of the universe. And here's the key part for our discussion on time. It's not just space that gets curved. Time does too. The closer you are to a massive object, the more space-time is curved, and the slower your clock will tick relative to someone far away. We talked about this before, but it's worth revisiting because it's the core of how time is not just a concept, but a physical property of the universe itself.
This leads to a really interesting open scientific mystery. What is the fundamental nature of space-time? Is it a continuous, smooth fabric, as Einstein envisioned? Or is it made of tiny, discrete units, like a digital photograph is made of pixels? This is the central question of quantum gravity, and it's a huge scholarly debate in physics. Many physicists believe that, at the smallest scales, the universe isn't continuous.
They think space-time might be quantized, meaning it's made up of tiny, indivisible packets of space and time. This would be a huge change to our understanding of the universe. It would mean that there's a smallest possible length of time and a smallest possible unit of space. So, while we experience space-time as a smooth, continuous thing, it's possible that, at the deepest level, it's a series of tiny, discrete moments and locations. It's a bit like watching a film from far away. It looks like a smooth, continuous motion. But if you zoom in close enough, you'll see that it's made of thousands of individual static frames.
Could our universe be the same? Is our experience of a smooth, flowing space-time just an illusion? A beautiful story told by countless tiny, discrete packets of reality? It's a question that gets at the very heart of what time is, and it's one we are a long way from answering. We've been talking about space-time as a flexible, four-dimensional fabric. But what happens when you stretch that fabric to its absolute limit? What happens in a place where gravity is so strong that it completely dominates the universe's rules? This is the world of black holes, and they are the ultimate space-time warps. Black holes are a mainstream science fact, and their effect on time is one of the most extreme and verifiable predictions of Einstein's theory of general relativity. A black hole is formed when a massive star collapses in on itself, crushing all of its mass into an incredibly small point called a singularity. The gravity at the singularity is so strong that it creates an area around it, called the event horizon, from which nothing, not even light, can escape. Once you cross that boundary, you're on a one-way trip to the singularity, and there's no getting out. But the real mind-bending part of a black hole isn't just what it does to space, it's what it does to time. From the perspective of an outside observer, as an object gets closer and closer to the event horizon of a black hole, it appears to slow down. Its clock ticks more and more slowly, and its light gets redshifted, meaning its light waves are stretched out to longer, redder wavelengths. As the object reaches the event horizon, its clock, from our perspective, appears to stop completely. It would look like the object is frozen in time, forever hovering just at the edge of the black hole, never quite crossing over. This is a beautiful and strange consequence of gravitational time dilation, and it's a perfect illustration of how gravity and time are linked. The closer you get to the black hole, the more space-time is curved, and the more time is stretched. At the event horizon, the curvature is so extreme that time, for all intents and purposes, grinds to a halt from an external point of view. But this leads to a huge, open scientific mystery. What does the person falling into the black hole experience? From their perspective, their clock would tick normally. They wouldn't feel like they were slowing down. They would cross the event horizon in a finite amount of their own time and continue on their journey. It's only to the outside observer that they appear to freeze.
So, does time actually stop at the event horizon, or is that just an illusion of our perspective? We don't know for sure, because we can't send a probe in and get the information out. The information is trapped inside, along with everything else.
This is a classic scholarly debate. Some physicists believe that the event horizon is a firewall, an area of incredibly high energy that would instantly incinerate anything that crosses it. Others believe that it's just a smooth boundary, and that the person falling in wouldn't notice a thing until they got to the singularity, where they would be spaghettified, a real scientific term, by the extreme tidal forces.
The mystery of what happens at the event horizon is one of the biggest puzzles in all of physics, and it's at the heart of the attempt to create a theory of quantum gravity that can unite the laws of the very large with the laws of the very small. Black holes are not just a cosmic curiosity, they are a laboratory for some of the most extreme physics in the universe, and their effect on time is a stark reminder that our intuitive sense of a steady, linear clock is a fragile illusion. We've stretched and warped time in black holes. But what if time itself wasn't a continuous flow, but a repeating, crystallized pattern? This isn't science fiction. It's the bizarre, new reality of time crystals. This is a relatively new scientific discovery, and it's a great example of an open scholarly debate. A time crystal is a state of matter that has a repeating pattern not just in space, like a regular crystal, but also in time. It's a structure that moves and changes in a predictable, repeating cycle without any external energy input. Let's break that down. You know what a regular crystal is, right? A diamond or a snowflake, for example. The atoms are arranged in a specific repeating pattern in space. A time crystal is similar, but it has this extra dimension of time. The atoms inside a time crystal are in a constant repeating motion, like a tiny metronome ticking back and forth. The amazing part is that it does this without any energy. It just keeps going, a perpetual motion machine at the quantum level. This is a mainstream science fact that has been proven in labs, a discovery so new that the Nobel Prize in Physics for it is probably just a matter of time.
This discovery is a huge deal because it challenges a fundamental law of physics, the second law of thermodynamics. Remember, that law says that the entropy of a system can only increase over time, or at best, stay the same. Things naturally move from order to disorder. A time crystal, with its perfect, repeating motion, seems to be a violation of this law. It's a system that has a perfect, unchanging order in time, without any energy being put in. How can this be? This is where the open scientific mystery and the scholarly debate come in. How do you reconcile a time crystal with the second law of thermodynamics? The answer, at least for now, is that time crystals are not completely isolated systems. They're what's called a non-equilibrium system. They are constantly interacting with the larger universe, and they are not in thermal equilibrium, meaning they aren't at the same temperature as their surroundings.
So, while the time crystal itself has a perfect repeating order, the entropy of the larger system it's a part of is still increasing. It's a bit like a tiny clock that's running perfectly on its own, but the room it's in is still getting messier.
The concept of time crystals also forces us to reevaluate our definition of time. Is time just a continuous flow, or can it be quantized and repeating? A time crystal's motion is not random. It's a specific repeating pattern. It's like finding a part of the universe that's not just a smooth flowing river, but a series of tiny, perfect waves. It suggests that time might have a deeper, more fundamental structure than we currently understand.
What are the implications of this? Well, the practical applications are still being explored, but they could be huge. Imagine a quantum computer that doesn't lose its coherence, or a clock that is so precise it never needs to be wound or powered. These are the kinds of things that time crystals might make possible. But for now, they are a powerful, strange, and beautiful reminder that the universe is far more complex than we give it credit for. Time isn't just a river, it's a landscape of mountains and valleys, and now, even perfect ticking crystals. So, time can be a crystal, and it can be stretched, warped, or maybe even non-existent. But for most of us, our relationship with time is a lot more mundane and, paradoxically, a lot more precise. We live in a world governed by digital time. This is a new concept in human history, one that has completely revolutionized our lives. Instead of relying on the sun or water clocks, we now use incredibly precise, universally coordinated clocks to keep track of every second. And the heart of this system is the atomic clock. An atomic clock is a device that measures time by monitoring the oscillations of a specific atom, most commonly cesium. The atom vibrates at a super-fast, perfectly regular rate, and we use these vibrations as our cosmic drumbeat. The official unit of time, the second, is now defined as exactly 9,192,631,770 oscillations of a cesium-133 atom. This is a mainstream science fact, and it has given us a level of precision that would have been unimaginable just a few generations ago.
These atomic clocks are kept in laboratories all over the world, and they are all synchronized to create a single global time called Coordinated Universal Time, or UTC. This is the time that is used to run our GPS systems, our financial markets, and our global communication networks. It's the time that your phone and computer are constantly syncing to. This is a brand new way of experiencing time, one that is not tied to the local position of the sun, but to the incredibly precise and universal rhythm of a single atom. But this new, hyper-precise digital time also leads to an interesting open scientific mystery. Our planet's rotation is not perfectly uniform. It's slowly slowing down over time due to the tidal forces of the moon, and it can speed up or slow down slightly due to things like earthquakes and atmospheric changes. Because of this, our atomic time, which is perfectly regular, and our astronomical time, which is based on the Earth's rotation, can get out of sync.
When the difference between the two gets too large, we have to add a leap second to our clocks to bring them back into alignment. This has led to a huge scholarly debate. Should we get rid of the leap second? On one side, you have the astronomers and those who want to keep our clocks synchronized with the rotation of the Earth. On the other side, you have the computer scientists and engineers who argue that the leap second is a nightmare for digital systems. It's a sudden, unpredictable change that can cause all sorts of bugs and problems. It's a debate between a human, biological need to be in sync with our planet and a technological need for perfect, uninterrupted precision. For now, the leap second is still with us, but its future is far from certain. So, while we've been talking about the big philosophical and scientific questions of time, remember that in your daily life, you are living in a world of digital time, a world of perfect atomic precision. It's a world where a clock is no longer a simple mechanical device, but a quantum measurement of the universe's most fundamental properties, and it's a world where our very definition of a second is a technological marvel that has fundamentally changed how we live, work, and communicate.
We've explored time in the context of atoms and planets, but now let's bring it back to a place we all understand: our human experience of time. This isn't about cosmic clocks or quantum mechanics. It's about the feeling of time. It's a mainstream science fact that our perception of time is not a fixed, universal thing. It can be stretched and shrunk by our emotions, our focus, and our age. This is a topic that sits at the intersection of psychology and neuroscience, and it has some wild and very relatable implications.
Have you ever noticed how time seems to speed up as you get older? When you were a kid, a summer holiday felt like an eternity. Now, a year can feel like it flashes by in a blink. Why is that? There's an ongoing scholarly debate about this, but one of the leading theories is that our brains measure time by how much new information we are taking in. As a child, the world is full of new experiences and new information. Everything is a discovery.
Your brain is working overtime to process all this novelty, and so it feels like a lot of time is passing. As we get older, our lives tend to become more routine. We've seen a lot of things before. Our brain doesn't have to work as hard to process the same old information, and so it feels like less time has passed. The days and weeks seem to blend into each other, and the years fly by.
Another great example of this is the phenomenon of boredom. When you're bored, your brain is actively looking for new information, for something to engage with. But since there's nothing new happening, it's constantly monitoring the passage of time. This makes every second feel like an eternity. On the other hand, when you're having fun, your brain is completely engaged in the activity. It's not paying attention to the clock at all. And so, when you look up, hours have gone by in what felt like minutes. This isn't just a feeling, it's a measurable effect in our brains. When we're engaged, our brains are using their resources to process the activity. When we're bored, those resources are redirected to the task of monitoring the passage of time. This also applies to situations of high stress or fear. Have you ever been in an accident or a dangerous situation where time seemed to slow down? People often report seeing things in slow motion, like every detail of the event is being captured in their mind. The scholarly debate here is whether time actually slows down for us, or if our brains are just processing information more quickly. The most accepted theory is the latter. In a stressful situation, your brain goes into hyperdrive, taking in and processing an incredible amount of information. It's like your brain is running a video at a higher frame rate. When you look back on the memory, it feels like it happened in slow motion because you have so much more detail than you would in a normal memory. It's a great example of how our brain's internal clock is not a fixed thing, but a flexible, adaptive system. So, while the atomic clocks are ticking along at a perfectly constant rate, your internal clock is a much more flexible and personal device. It's a clock that is tied to your emotions, your experiences, and your memories. It's a clock that can speed up when you're having fun and slow down when you're bored. It's a great reminder that time is not just an external, objective force. It's also a deeply personal, subjective experience.
We've talked about how our brains create our subjective experience of time, but what about things that seem to exist outside of time entirely? This is a philosophical idea that has been debated for millennia. Is there anything in the universe that is truly timeless? This is a deep and open scholarly debate, and it forces us to confront the very definition of reality. Let's start with a classic example: mathematical truths. The number 2 has always existed. The concept of a triangle has always existed. It doesn't matter if there's a universe or not. The laws of mathematics would still be true. 2 plus 2 would still equal 4. The angles of a triangle would still add up to 180 degrees. These truths don't change over time. They don't have a past, present, or future. They just are.
So, are they timeless? This is a popular view in the philosophy of mathematics, and it suggests that there is a realm of reality that exists outside of our four-dimensional space-time. It's a world of pure, abstract truths that are not subject to the laws of physics, including the law of time.
This leads to a really interesting debate about Platonism. This is the philosophical idea that abstract concepts, like numbers and ideas, exist in a timeless, non-physical realm. We don't invent these concepts. We discover them. It's a bit like an explorer finding a new continent. The continent was always there. We just hadn't seen it yet. So, in this view, the universe is not just the physical world we see and touch.
It's also a timeless world of ideas and concepts that are just as real, if not more so, than the physical world.
Another great example is the concept of God in many religions and philosophies. In many traditions, God is seen as being outside of time. God is not a being that exists in a before and after sequence. God is an eternal, timeless reality. God doesn't wait for things to happen. All of time, the past, the present, and the future, is equally present to God. This is a view that is not based on scientific proof, but on faith and philosophy. But it's a powerful and elegant idea that suggests a reality that is not limited by the same constraints that we are. So, is there anything truly timeless? This is a question that we can't answer with a scientific experiment. It's a question that we have to grapple with using logic and philosophy. On one hand, everything we see and touch in the physical world is subject to time. Stars are born and die. People are born and die. The universe itself had a beginning and will have an end. On the other hand, there seems to be a realm of reality, a world of abstract truths and ideas that seems to exist outside of this flow. It's a mainstream science fact that our physical universe is governed by the laws of time, but it's an open scholarly debate whether those laws are the only laws there are. So, when you're lying in bed tonight, thinking about all this, think about the timeless truths that govern our universe. Think about the numbers and the ideas that have always been there. It's a great way to put our own fleeting lives into a larger and maybe a timeless perspective. We've talked about timeless ideas and cosmic clocks, but let's be honest, for most of human history, time wasn't a scientific concept at all. It was a human invention, a tool we created to order our lives. This is a mainstream science fact that's often overlooked. The idea of a perfectly consistent universal time, a time that we can measure in seconds, minutes, and hours, is a relatively new invention. Think about how our ancestors experienced time. Their clocks were the sun and the moon. The day was measured by the position of the sun in the sky. The year was measured by the changing of the seasons. Time wasn't a uniform, abstract thing. It was a cyclical, natural rhythm. The concept of a universal hour didn't exist. An hour in winter was a different length than an hour in summer. Life was governed by the rhythms of nature, not by the ticking of a clock. The idea of waking up at a specific time and going to work at a specific time and getting paid for a specific number of hours of labor is a modern invention. The invention of the mechanical clock in the Middle Ages was a huge turning point. For the first time, humans had a way to measure time independently of the sun. But even then, time was local. Noon in one city was not the same as noon in another. It was only with the invention of the railroad in the 19th century that we needed to create a universal, standardized time. To make a train schedule that worked across a continent, you couldn't have every city running on its own local time.
So, we invented time zones. This is a great example of how time is not just a physical property of the universe, but a social construct. We needed to create a uniform time to make our society run smoothly.
This leads to a really interesting, open scholarly debate. Is time a fundamental property of reality, or is it a social construct? The scientific community is largely in agreement that time is a fundamental property. Einstein's theories and the laws of thermodynamics all point to a physical reality of time. But philosophers and sociologists have a different take. They argue that while there might be a physical reality of cause and effect, the way we experience and measure time is a social construct. The minute, the hour, the day, the year, these are all human inventions. A dog doesn't know what time it is and a tree doesn't care. It's a human way of organizing and making sense of the world.
So, while we've been talking about the deep, cosmic mysteries of time, remember that our everyday experience of time is a very human thing. It's a thing we invented to make our lives easier, and it's a thing that has become so ingrained in our lives that we often forget it's not a natural law. It's a beautiful paradox, a scientific reality that is also, in a very real way, a human invention.
We've talked about time as a human invention, but now let's go back to one of the most fundamental and uninvented facts of the universe, the speed of light. This is a mainstream science fact that is at the heart of our understanding of time and causality. The speed of light in a vacuum, roughly 186,000 miles per second, is not just a speed, it's a cosmic speed limit. Nothing with mass can go faster than the speed of light. But why is it so important for our understanding of time?
The key insight from Einstein's theory of relativity is that the speed of light is the ultimate constant in the universe. It's the same for everyone, no matter how fast they are moving. This seems impossible, right? If you're in a car going 60 miles an hour and you throw a ball forward at 10 miles an hour, the person watching you sees the ball going at 70 miles an hour. It's just simple addition. But with light, it doesn't work that way. If you shine a flashlight in a spaceship going at 100,000 miles per second, the light will still travel at 186,000 miles per second. The speeds don't add up. To make this work, something else has to give, and that something is time and space.
This is where the concept of causality comes in. Causality is the idea that a cause must come before its effect. If you hit a billiard ball, the ball moves after you hit it, not before. The speed of light sets the ultimate limit on this. For one event to cause another, the information about the first event has to travel to the second event. And the fastest that information can travel is the speed of light. This creates a causal structure for the universe. It means that there is a defined past that can affect a future, and a future that cannot affect the past. This is a huge reason why traveling to the past is so difficult to imagine. If you could send a signal faster than the speed of light, you could send a message to the past and you could break causality, which is one of the most fundamental rules of the universe. But this leads to a really interesting open scientific mystery and scholarly debate. Are there things that can break the speed of light barrier? There are some weird things in the universe that seem to move faster than light, but on closer inspection, they don't break the rule. For example, the expansion of the universe itself can cause galaxies to move away from each other faster than the speed of light. But this isn't a physical object moving through space, it's the space between them expanding. Another example is the strange phenomenon of quantum entanglement, where two particles seem to communicate instantaneously. But, as we've discussed, this doesn't allow for the transfer of information faster than light, so causality is preserved. However, there are still some who wonder if the speed of light is the ultimate constant. Could there be a way to create a wormhole, a shortcut through space-time, that would allow for faster than light travel? Or could there be a deeper, more fundamental law that we haven't discovered yet? For now, the speed of light remains the cosmic speed limit, and it's the law that gives time its direction and its structure.
It's the law that tells us that the universe is a story unfolding and that the past, for all its mysteries, is truly gone.
We've just talked about the ultimate cosmic speed limit and how it gives time its structure. Now let's revisit one of the most beautiful and verifiable consequences of that limit: time dilation. This isn't just a theoretical curiosity, it's a proven mainstream science fact that we have to account for in our daily lives. It's the idea that time passes more slowly for an object in motion relative to an observer. The faster you go, the slower your clock ticks. The best real-world example of this is the Global Positioning System, or GPS. The GPS satellites that orbit the Earth are moving at speeds of about 14,000 kilometers per hour. According to Einstein's theory of special relativity, this high speed causes their clocks to tick a little bit slower than clocks on Earth. But that's not all. The satellites are also in a weaker gravitational field than we are on the surface of the planet.
According to Einstein's theory of general relativity, this weaker gravity causes their clocks to tick a little bit faster than ours. These two effects, the time dilation from speed and the time dilation from gravity, are working against each other.
The effect of gravity is actually stronger than the effect of speed, so the net result is that the clocks on the satellites tick about 38 microseconds faster than clocks on the ground every day. That's a tiny, tiny amount, but if we didn't correct for it, the GPS system would be off by several miles every single day.
So, every time you use your phone to navigate to a new coffee shop, you are, in a very real way, using a system that is constantly accounting for the bizarre and beautiful nature of time dilation. It's a great example of how a mind-bending theoretical idea has become a practical, everyday reality.
But this also leads to an open scientific mystery and a scholarly debate. We've proven that time dilation is real. We've measured it in laboratories and on satellites. But what is the true nature of the time that is being dilated? Is it just a property of the clock itself? Or is it the fundamental physical property of the space-time that the clock is moving through? In other words, is the time on the clock actually slowing down, or is it just the process of timekeeping that is being affected?
The most accepted view is that time itself is being dilated. Time is not a separate, external force. It's a dimension, and its flow is a property of the universe that can be affected by speed and gravity. A clock that is ticking slower isn't a broken clock. It's a clock that is accurately measuring the passage of time in its own reference frame. But the philosophical debate continues. Is our experience of time just an illusion? And is the true nature of time a static, timeless block? Or is the flow of time a real, physical process that can be stretched and shrunk by the very fabric of the universe? It's a question that gets at the heart of our understanding of what time is, and it's a question that's still very much up for grabs.
We've reached the end of our journey, and we've explored the weird and wonderful world of time from every angle. We've seen how it can be a static, unchanging block and a fluid, flexible dimension. We've seen how our brains create our personal sense of time, and how the universe's grand clock is marching toward a mysterious end. But the biggest mystery is still unsolved. Ultimately, we don't know if time is a fundamental reality or an emergent property.
Let's quickly recap the two main schools of thought. On one side, you have the view that time is a fundamental, physical property of the universe. It's a real dimension, just like space, and it's something that we can measure and manipulate. This view is supported by Einstein's theories of relativity, which show that time can be stretched and warped. It's a physical reality, and our experience of it is a direct consequence of that reality. In this view, the arrow of time, the fact that time moves forward, is also a fundamental property, perhaps tied to the second law of thermodynamics. The past is gone, the future is yet to be, and the present is the moment we are in. On the other side, you have the view that time is not a fundamental property of the universe at all. It's a concept that emerges from the behavior of a vast number of particles acting together. In this view, at the deepest level, the universe is timeless, a static, unchanging thing. The equations of quantum mechanics, which don't have a special direction for time, seem to support this idea. The arrow of time, the feeling of a flowing present, and our memories of the past are all just features of our consciousness, a cognitive trick that helps us make sense of a reality that is, in its true form, timeless.
This is a huge open scholarly debate, and it is at the heart of the attempt to create a theory of quantum gravity that can unite general relativity and quantum mechanics. The two theories, in their current form, are in deep conflict over the nature of time. General relativity treats time as a flexible dimension, while quantum mechanics, in some interpretations, suggests it doesn't exist at all. Finding a way to reconcile these two views is the holy grail of modern physics.
It's the key to understanding the very nature of reality. So, where does that leave us? We don't have an answer. We have two incredibly powerful and incredibly different ways of looking at the universe, and they can't both be right. The mystery of whether time is real or an illusion is a mystery that is as old as human thought itself, and it's a mystery that is still waiting to be solved. So, as you drift off to sleep tonight, remember that the clock on your wall is just one way of measuring the universe. The true nature of time might be something far more beautiful, far more complex, and far stranger than we can possibly imagine. The mystery is still there, waiting for us to figure it out.
We've been on a long journey together, haven't we? From the mind-bending depths of black holes to the strange, crystalline ticking of atoms. We've stretched our minds around concepts that defy our everyday understanding and gazed at a universe that is far more complex and beautiful than we ever imagined. As we wind down, let's just sit for a moment with some of these ideas. Feel the weight of the universe's grand clock ticking forward from a mysterious beginning to a quiet, cold end.
And then, feel the gentle personal rhythm of your own life, the beat of your heart, the rise and fall of your breath. Remember that the time you feel, the steady march of seconds and minutes, is a beautiful and elegant illusion created by your own brain. The past is not a lost country. It's a story you tell yourself, a collection of memories woven into a personal narrative. The future is not a destination, it's an open road, full of possibilities that you, in your own way, get to help create. And the present moment, that fleeting instant that is gone the moment you experience it, is the most precious thing you have. It's all there is. It's where the magic happens, where you get to experience the universe, even if just for a little while. So, as you settle in, and the world outside begins to fade, let's take a deep breath together. Breathe in all the cosmic dust and starlight we've been talking about, and breathe out all the worries and the noise of the day. Feel the comfort of your bed and the stillness of the room. The world is a weird and wonderful place, and you are a weird and wonderful part of it. The questions we've been asking tonight are not meant to give you a headache. They're meant to fill you with a sense of wonder, a feeling of awe for a universe that is so much more than meets the eye. The universe's time might be marching on, but right now, your time is your own. It's a time for rest, for peace, and for dreams. So, let your mind drift away from all the paradoxes and the paradoxes. Let yourself be carried away by the gentle flow of sleep. Good night.